Hello everyone, thank you for being here today. My name is Shivashakti and I'm excited to present to you the entity relationship model. My group consists of 4 members, including myself, Shivashakti, Divyashri, Chua Ji Yuan, and Tan Poshit. Over the next few minutes, we'll explore the entity relationship model in detail. We'll cover key concepts such as entities, attributes, and relationship. Let's dive right in. Now, what exactly is the entity relationship model? Think of it as a blueprint for a database. It provides a conceptual representation of data and helps us define its key components. First, we have entities, which are the objects or concepts we want to represent, like a student or a course. Next, we have attributes, which describe the properties of these entities. For example, a student might have attributes like their name or ID, and a course might have attributes like its title or duration. Finally, we have relationships, which define how entities are connected. For instance, a student enrolling in a course is an example of a relationship. Each of these components work together to provide a clear, structured view of the data, making it easier to design and manage databases. Let's now dive deeper into the concept of entities. In database terms, an entity doesn't refer to a single occurrence of an object, but to an entire entity set, essentially a collection of similar objects. For example, instead of one student, it represents a table that includes all students. In relational database environments, entities correspond to a table rather than a specific row. When working with ER models like the Chan or Crow's-Foot models, entities are represented by rectangles. Inside these rectangles, we write the entity's name, which is always a noun and written in capital letters. This consistent structure helps us visually represent and organize data in a meaningful way. I'll pass it over to Divyashri.
Move on to attributes. In the ER model, attributes are essential properties that defines the characteristics of entities, and they come in various types that help us model data more precisely. Simple attributes are atomic and cannot be broken down into smaller parts. An example is student ID, which serves as a unique identifier for a student and stands alone without further subdivision. On the other hand, composite attributes can be divided into smaller, meaningful components. For instance, name is a composite attribute because it can be split into first name and last name. Single value attributes can only hold one value per entity. For example, a student can only have one CGPA at any given time. So, this attribute is a single valued. Lastly, multi-value attributes are those that can hold multiple values, such as address, which can consist of several components like number, street, postcode, city, and country, reflecting the fact that one person may have more than one address. By understanding these different attribute types, database designers can create more organized, efficient, and scalable data models that capture the true complexity of real-world data. This is an example for a multi-valued attribute. In the entity relationship ER model, relationships defines how entities are connected and participants in these relationships are the entities that take part in them. These relationships always operate in both directions, meaning that if one entity is related to another, the reverse connection also exists. Relationships can be classified into three types based on how entities are linked: one to many, one to one, and many to many. For example, in a one to many relationship, one entity like a teacher can be linked to multiple students, whereas in a one to one relationship, one entity such as a person might be associated with exactly one passport. A many to many relationship, like a student enrolling in many courses, shows that multiple instances of both entities are involved. However, determining the classification of a relationship can be challenging if only one side of the relationship is known as the nature of connection, often requires understanding both entities involved. And that's all from me.
The process of database design is an iterative rather than a linear process. It usually begins with a general narrative of the organization, operation, and procedures. The process is repeated until the end user and designer agree that the ER diagram is perfect. Now, let's look the example, Penny College database. First, it can be divided into different schools, while each school has a professor sitting as a dean. And also, each school has several departments. The number of departments may be 1 to undefined. For each department, we'll have professor assigned to it and one of them will chair the department. After that, each department may offer several courses and several class sessions of the same course, and the department's advisor may consult several students. Each professor may teach up to 4 classes. For students, they will enroll in several classes but only once during any enrollment period. After that, each student shall only have one major associated with one department. And this is the full ER diagram example. To mapping an ER model into a relational model, it has 5 steps involved, which is strong entities, weak entities, supertype or subtype relationship, binary relationship, ternary and higher degree relationship.
Next is artist database as an example. We have three entities here. They are painter, painting, and gallery with each attribute represented in the table. The relationship between these entities is a painter can create multiple paintings, so this forms a one-to-many relationship. Second is painting may be exhibited in multiple galleries. Thus, this forms a many-to-many relationship. So, to make this relationship into a relational model, we have to create a new entity, which is a composite key to connect these two entities. This is essential for accurately representing many-to-many relationship without duplicating data. Next is database challenges design. First is conflicting goals. Database designers often face conflicting goals such as adherence to design standards. Design standards are important for developing logical structure that minimize redundancy. And next is processing speed and information requirements. High processing speeds and complex information needs may require compromise such as combining tables. And second is for design consideration, which are logical requirements and design conventions, processing requirements, operational requirements, documentation, and end-user requirements such as performance, security, shared access, and data integrity. So, as a conclusion, the ER model is a vital tool for conceptual representation of data. Mapping ER model to relational model to ensure logical data organization, and it is widely used in various fields, such as banking system and e-commerce system. And a well-designed database avoids redundancy, maintains consistency, and enhances the performance. So that's all for our presentation. Thank you.